Okay, awesome. So we're going to run through the laws or rules of exponents multiplication rule. So on your paper, follow along. I'm going to do a to the x power times a to the y power. And anytime we multiply exponents that have the same base, so a and a, we add the exponents. So this would give us a to the x plus y. Awesome. All right. Division rule. If we have a to the x power divided by a to the y power, so either that's going to have the division symbol or it might be written as a fraction. That's how I'm going to write it. A to the y power on the bottom. Then that division sign, I'm going to color code it here. This becomes our subtraction sign. And so now we have a, since we have a common base, x minus y. That's our division rule. Now we have, yeah, absolutely. Right there. So a to the x divided by a to the y, and then we subtract the exponents because of the division rule. Awesome. Now we have two power rules. We have the power of a power rule, and then we have the power of a product rule, which is essentially just distribution. Now our power of a power rule would be like if we have a to the x power in parentheses raised to the y power, like this. In which case, a power to a power means we multiply. And so that gives us a to the x y power. Okay. Now our second power rule is the power of a product rule, aka distribution. And that would be if we had, say, two variables or a coefficient and a variable. So I'm going to write it both ways. I'm going to say we have ab to the x power, or we have 2b to the x power, right? Just so you can visualize both with a coefficient and with a variable. In that case, we take the x power and we're just distributing it to whatever is inside of the parentheses. So that would give us either a to the x power times b to the x power, or using the coefficient example, 2 to the x power times b to the x power. Okay. Now I want to show a difference because this is commonly a mistake that I've seen with students, young students. I'm going to put in 2b raised to the x power versus 2b without parentheses to the x power. So you see how I've written that here?
Yes.
Okay, perfect. Now, which one of these are we going to distribute with? The one with parentheses or the one without?
The one without.
Do we want to distribute without or we want to distribute with?
Without.
With. We want to distribute with. So the first one, just like the example on the last page, we distribute the x power and we get 2 to the x times b to the x versus 2b to the x, which actually just stays the same because there's nothing to distribute in that case. So you see that there?
Yes.
Okay, awesome. Now we have it's called the power of a fraction rule, but really it's just distribution again, okay? So say we have a fraction, because it's just like it's similar to the division rule, except that it's the same exponent. That's the only difference. So I'm going to compare the two. So if I have a over b to the x power versus a to the x power over a to the y power. So first notice the difference in the two problems, okay? Here we have a fraction, with a unique numerator and a unique denominator, raised to the same power. Okay?
Okay.
So think of everything within the parentheses here as one entity. So it could be a number with a variable, two variables, it could be anything, right? But it's one entity, and we're going to distribute the x to both the top and the bottom.
Okay.
And then that's going to give us a to the x over b to the x, like this. Okay? Versus the other side, where we have the same base, but two different exponents. Okay? In which case, we keep the base, and then we apply our division rule, which, remember, if we have a fraction bar, it turns into a handy-dandy minus sign, and we end up with a to the x minus y. So you see how those are very different problems?
Yes.
Even though they don't look that different on paper. So that's why with the exponent rules, the trick here to doing well with exponents and logarithms is to be very meticulous, very careful about how you're rewriting the problems and making sure that you're applying the most appropriate rule. Okay? None of the rules are very difficult. They just take practice. Okay? And then let's take a look at, so the zero exponent, my absolute favorite. Anything in the entire universe to the zero power is always equal to 1. So a to the zero power is equal to 1. 2,496 to the zero power is equal to 1. If you could have negative infinity to the zero power, it would be equal to 1. All right. And then anything to the first power is always itself. So if I have a to the first power, it's equal to a.
Okay.
You'll see this. These are very handy rules when you start doing logs, because you'll see like log base a of a is equal to 1. So you'll see a lot of those rules come up. And then my last two, and probably some of my favorites, the negative exponent rule. So I'm going to actually show you this two ways, above the fraction bar and below the fraction bar. So if I have a to the negative x power, I'm going to highlight that negative sign. That becomes my fraction bar. And I just put a 1 on top. And I rewrite everything as is. So then I have a to the x power. So we got rid of the negative. It became the fraction bar. You see I color-coded it there. And then we just drop the a to the x underneath of the fraction bar. So we get 1 over a to the x. Does that make sense? Okay, awesome. Awesome. Now, if we have a negative in the denominator, that's okay too. We still flip it over the fraction bar. We just have to make the fraction. We just have to remember that we're going to lose the fraction bar in the final answer. So say I have 1 over a to the negative b power, right? And I'm going to highlight this, the negative and the fraction bar, right? Because now we have both, right? And so just like if you have a negative times a negative, it gives you a positive, right? So think of it like that. I've got two negatives essentially in here because that fraction bar means we moved it, right?
Yeah.
In this case, we're going to flip it over the fraction bar. So now I'm going to have the 1 on the bottom, and I'm going to have the a to the b on the top. And so in the numerator, we don't need the 1 on the bottom, so our final answer is just a to the b power.
Okay.
Okay, awesome. And then last but not least, the fractional exponent, aka our radical rule, where I always compare it to the radical that most people are comfortable with because of quadratic equations. So if we take the square, well, not square root, if we take the radical, or I guess technically square root, of a to the x power, right? And I'm going to put a y on the outside. So normally you would see something like square root of x to the third power, right? That's normal. And we know as seasoned math students, that there's an imaginary 2 on the outside of that radical. Like that, right?
Yes.
Okay. And if I were to rewrite this as a fraction, then I would get x, whoops, and I would raise it to a power where I have 3 in the numerator and I have 2 in the denominator. So whatever's outside of the radical becomes the denominator. Whatever's inside the radical with the number or the variable becomes the numerator.
Okay.
Okay. So then if I go and I look back at my other side, that means that a to the x power underneath of the radical, right? So we have y, the y root of a to the x power, then becomes a to the x goes to the numerator, and the y goes to the denominator. So a to the xy, like that.
Okay.
Okay. Now, those are all of the exponent rules. So if you're going through practicing those, either write them over repeatedly, make flashcards, whatever you need to do to make sure you've got those down solid, because a lot of those rules will translate into the logarithm rules. That's why they're super important to understand now. And that's why I really went through them very slowly to make sure that you can see the comparisons and see where students typically get confused. So the ones that can be confusing, those are the ones where it's this versus that. So you can clearly see the difference and understand, okay, when do I apply this rule and when do I apply a different rule, even though the problem looks pretty similar. Make sense?
Yeah.
Okay, awesome. So I want to walk you through just a couple of problems. So I'm going to do these in pretty pink. And usually the negatives are pretty uncomfortable, so I'm going to do a to the negative 2 power times b to the 4th power over c to the negative 3rd power. So we've got our problem, a to the negative 2nd times b to the 4th over c to the negative 3rd. Now this can look intimidating, but it's not. So remember, we have 2 rules here, right? All of the variables are different, so we don't have to worry about multiplying any of those exponents together. So that's a relief, right? The only 2 rules we're going to apply here are the division rule and the negative exponent rule. And so if we go ahead and the easiest one to apply first is the negative exponent rule, because remember, we're just flipping it over the bar. And I like to think of it that way because it really does make it pretty simple. So our a to the negative 2nd and our c to the negative 3rd, they're just going to switch sides, right? So we're going to I'm going to keep them in alphabetical order. So I'm going to keep my b to the 4th, make that in the front. And then c to the 3rd will move up. And then a to the 2nd will move down. So now we've gotten rid of all of our negatives, right? Okay, awesome. Now, if we had any numbers at all, then we might be able to apply the division rule, but it actually turns out we don't need it here. So I spoke too quickly. And that's another thing. You always want to assess each step of the way to make sure that you're doing the right thing, as we just did. Otherwise, we would have applied a rule that we don't even need.
Okay.
Okay, so we're actually done. That's the final answer. This is the most simple version of this problem.
Okay.
If we had a b in the top and a b in the bottom or anything like that, any of the same 2 variables, then we would apply the division rule, because then you'd have a common base and you would go ahead and subtract the exponents, but we can't do that here because all of the variables are different. Is that clear?
Yes.
Okay, awesome. Now let me show you this also. If we have, oh, here's a good one. If we have a really big problem, just like with any fractions, we can break them into pieces. And I like to rewrite the problems and divvy them up according to variables. So let's say we have this huge wonky problem like 20x squared y to the 6 all over 5x y to the 3rd all to the 2nd power, right? So we've got this humongo problem.
I can't see you.
Oh, no worries. Let me do this. Just hang tight. You'll see it as soon as I upload the link, okay? But just you can hear me, right? Okay, just keep listening. All right, so what we would do is I'm putting this one on the board for you. We are going to do coefficients. Then we're going to do one variable. Then we're going to do the other variable. And we're going to simplify in pieces as we go along. Make sense?
Yes.
Okay. And so that's our problem. And so remember, everything is inside of the parentheses. So at the end, once we finish simplifying within the parentheses, then we're going to do the exponent, just like order of operations. So you still have to apply order of operations. I know you thought you were over sixth grade math, but you're not. It still applies, right? So we're going to do parentheses first, then exponents. So I'm going to color code this. Now, first thing I would do is the coefficients. And this one actually simplifies really well. So 20 divided by 5, that would give us 4 on the top, right? And so I'm going to go ahead and rewrite that 4 in there. And I'm going to go ahead and put my fraction bar in here just so I know where things are going, okay? So we've got 20 divided by 5, which gave us the 4. Now we have x squared over x, right? And remember, now we have a common base and 2 exponents. So 2 minus 1, because we have x squared minus 1, right? Because we have a common base. That leaves us with just 1x on the top, right?
Yes.
Okay, so we leave the x on the top where it is, in the numerator. Now, we get to the y's. And just for fun, what I'm going to do is I'm actually going to switch these for you just so you can have an example of this. I'm going to switch the 6 and the 3. So now I have y to the third on the top and y to the 6 on the bottom. And I did that just so you can get a good example of this. If this were the case, we're still going to do the same division rule. We have a common base, right, with different exponents. Even if they were the same exponent, we're still going to do the same thing as long as we have a common base. So we have y to the third minus 6, right? I like to look at it within the frame. We have the bigger number on the bottom, and remember, we're just canceling out. So we've got 3 on the top. That subtracts from the 6 in the bottom. So we have 3 left on the bottom, right?
Yes.
And so we keep that on the bottom because there's no negatives here the way that we've done it, right? So we have y to the third on the bottom. Makes sense? It would only be y to the negative third here if we kept everything in the numerator. Okay? But the way we did it, we just canceled out 3 on the top, and we took out 3 on the bottom. And so we're still left with a positive exponent. Now we've simplified. Isn't that a much cleaner problem? Instead of 20x squared y to the 6 over 5x y to the third and then having to square that whole thing. Yikes, right? Now we've just got this. This is cute and easy. Okay? We keep our 2. And now, because everything's within the parentheses still, now we want to distribute the 2 to the 3 constituents. So this is going to give us 4 squared, which is
4 squared is just 16.
perfect. So we've got 16 on top. And then x squared. And then what does y cubed to the second power become?
Wait, say that again?
The bottom. So y cubed to the second power.
So it would just be 1, y to the 5th power.
Y to the power to a power gets multiplied or added?
Multiplied.
Multiplied. Very good. So then this becomes y to the 6th power.
Okay.
Okay, and now we have 2 different variables. We have a coefficient. Can we do anything else to simplify this?
No.
No. We're done. This is perfect.
Okay.
Okay, so notice we're going to go back to the original problem because I switched the 6 and the 3. So the only difference, right, would be that your y to the 6 would be on the top.
Okay.
Okay? So that's how you break down those big problems. I would go back, review the steps, go back through the pages where you can see the comparisons, okay, to make sure you understand the comparisons. Make sure you can understand how to rewrite those radicals into the fractional exponent form. Remember those identity rules and the zero exponent rule. And then this is just practice, practice, practice. The other thing that you're reviewing within this unit is scientific notation and I think also standard notation. And so scientific notation has a whole nother set of rules. So the next few weeks, it's going to be a lot of memorizing rules. So it's just going to be going through them, repetition. That's all math is. It's mental muscle memory. Okay? Triple M's. Mental muscle memory. That's a tongue twister. Give me $5 if you can say it 20 times fast. Just kidding. You don't want to do that. So just practice that. I will definitely see you next week. If you have any questions in between now and then, just shoot me a text message or email me, and I will either make you another video or we'll jump into a session and we'll do a one-on-one. Sound good?
Okay, that sounds good.
Awesome, Sash. You did really, really great. Put this into practice. Congrats on your 100. I'm super proud of you. And keep up the good work. I'll see you next week.
Okay, thank you.
Yo.
This video will be, you'll send it to me?
I will. Yep, I'll upload it onto my YouTube channel, and then you'll be able to access it from there. And I'll send you the link.
Okay, great, thank you.
You're welcome, dear. Have a good night.
You too, bye.
Bye.